We're going to start today further back than that. Does somebody have a stylus I can borrow? Mine has apparently just decided to stop working. Do you have an extra one? I would appreciate it if somebody had one I could borrow. I'd be happy. Thank you. I really appreciate it. I'll be ready to go next time. All right, so we're going to be starting all the way back and review some topics from our Algebra 2 class and then see a little bit of extension there. But a lot of what we do today is going to be things that we did in your Algebra 2 class, so it should feel rather familiar for pieces of it. And I'll probably ask you to remember that you could have remembered some stuff, and maybe some of it will be like, oh yeah, I remember that. Some of it will be like, oh, that sounds familiar. And some of them might be like, ooh. Don't worry too much about that. It'll all be fine. But we're going to start today in Chapter 1. Chapter 1 is reviewing some concepts regarding functions. So we'll start with just the general definition here, our most basic definition from our algebra class with a function. So we say that a function is a set of ordered pairs where the inputs come from a set D. We often call that set the domain. And the outputs come from some set R that we often call the range, such that every member of D is paired with exactly one member of R. We'll take a few minutes here and talk about a couple of different ways we represented functions, and or that we can represent functions, and look at some of those representations and decide whether they're a function or not. Talk about how we did that. This should be familiar sounding. It was really kind of the start of Algebra 2 last year. So we'll look at some examples now and just make the decision whether something's a function or not. So our first representation we'll talk about is the mapping diagram. So the mapping diagram, we have two circles or ovals, and then we'll put like a dot for each of the members of those sets. So I'm going to just be general and call them like x1, x2, x3, and y1, y2, y3, but they would be numbers. So then what we do is we draw some arrows to indicate what or how the pairs or how things are paired. So we have something like this, where x1 is paired with y2 and x2 is paired with y1 and x3 was paired with y3. Let's just kind of walk through the definition here and check to see whether this represents a function or not. So the definition has two parts. It says that every member of D is paired. So if I look through, each one of those three is paired with something else. And then I have to make sure that it's paired with exactly one thing. So because they all just have one arrow originating from them, we know they're paired with exactly one thing. So this would represent a function. Everybody good with that idea? Okay. Let's look at a couple more examples of this just to make sure that we got it. And then we'll move on to something or another representation. So let's say we have a domain and range and say something like this. Does this represent a function? No, why not?
Because not every domain factor has a range partner.
Yeah, x3 isn't paired with anything, right? If I wanted to make this a function, I could do something like that. If I added that arrow, then it would represent a function, right? Does it matter that we have a y that's unpaired? No. If you want something to be a function, all we care about are the domains, right? Okay. So again, that blue mark is just like hypothetical. Just illustrate the difference between an example that is not a function to an example that is a function. Like what change would I need to make? You know what I mean, guys? Again, these concepts are largely review, so we'll be a little informal and just kind of draw some examples and talk about them a little bit. What if I have something like this? Is that representing a function? No. What's the problem? Yeah, the specifically which domain? X1, right? So one way I could make this into a function would be to just get rid of one of those arrows, right? That are coming out X1. Does it matter which one I get rid of? No. So everybody happy there? Good. That tends to be a relatively easy to deal with representation. Let's look at another one. So another way that we can represent a function is with a formula or an equation. Oops. So what if we ask, does the formula y equals x squared plus 2 define y as a function of x? So what's this little extra at the end? Why didn't I just ask, is y equals x squared plus 2 a function? What am I getting out? What should you be getting out of that extra little piece at the end? Yes, sir.
Well, potentially, like you could say that x could be a function of y. So by specifying it, you're specifically saying that x or that y would be a function of x.
Yeah, you're basically giving the independent dependent variable, right? If I don't do that, it's not entirely clear which one is the independent variable, which one is the dependent variable. And it would make a difference in this case. One would be a function, one would not. This turns out to saying y is a function of x, says that x is the independent variable and y is the dependent variable, which is our default assumption all throughout Algebra 2. When we wrote like y equals x, we assumed that like x was the independent variable and y is the dependent variable, right? So oftentimes when we're looking at a formula, it's not always entirely clear whether it represents a function or not, right? Could we change the form to make it easier to tell? What would be a form that would make it easier to tell if this is a function or not? What could we do to tell if that's a function? Graphing it, right? And that's something that's relatively easy to do. And now I don't even need a super precise graph of this. I can use kind of what I know about the formula that I see here to sketch a graph that'll be good enough to answer this question. So if I look at y equals x squared plus 2, what kind of formula is that? Well, it's not a slope-intercept equation because it's not 2x plus 2. It's x squared, right? So what is this then?
parabola?
Okay, it's quadratic,
Okay.
and the shape of a quadratic is a parabola, which is where we're going. You're just one step ahead, but that's good. Everybody's recognized that? So a parabola is either going to open up or open down. Do you remember how to tell if it opens up versus opening down? Great. So the leading coefficient is positive, it'll open up. If a leading coefficient is negative, it would open down. In this case, our leading coefficient is 1. We have 1x squared. So our parabola would be opening up. What does the plus 2 at the end do here? Yeah, it's the y-intercept, or just moves it up 2 units, right? Very good. So, I don't know. It'll look something like this, right? Everybody happy there? So now we have a graph instead of a formula. Now, if you didn't remember any of those things, how could have you gotten that graph also? Calculator, right? You could type in your calculator and ask it to graph it if you weren't sure what the shape was going to look like. Although this is pretty reasonable expectation for the honors class that you're able to look at that and go, okay, it's a parabola going to look kind of like this. You know, that's pointing the right way and it's above the x-axis. I would be happy with almost anything you did there. So once we have our graph like this, how do we tell if it's a function or not? Go ahead, Sydney.
Vertical line test?
Yeah, the vertical line test. So what we're looking for in the vertical line test is we're checking to see, are there any places where I draw a vertical line that that vertical line would intersect the function more than once, right? In this case, the answer here is no. So this would represent a function. Everybody's happy with that? This tends to be a pretty sticky idea. Students are usually pretty good about this and remember that test pretty well because it has a nice name that tells you exactly what it's doing. What if we had something that looked like this? Is that a function? No. So easy to see that there is lots of places where I can draw a vertical line and the graph is intersected more than once. Does it matter that there's also a place where I can draw a vertical line where it's intersected exactly once? No. All I need is one place where it fails the vertical line test to say it's not a function. Just one place. Doesn't matter if there's lots of places where the vertical line test passes or the vertical line intersects only once. One failure is failure for the whole thing, right? We feel good about graphs? That's pretty easy, right? The final representation that we had was function notation. Well, the final one we'll talk about anyways, is function notation. And this is really not dissimilar from just writing a formula. So like function notation is like, you know, y equals f of x or f of x equals yada, yada, yada. It's basically saying that y is the value of the function f at x. And the advantage of function notation is there's no ambiguity about which one is the independent or dependent variable, like we had when y equals x squared plus 2. Here we're told that y is expressly dependent on x because of the notation involved. Everybody's okay with that? So that's the main advantage, is just it adds a little layer of clarity as to what's the independent versus the dependent variable. But there's also some like notational advantage here. So like, say we have the function f of x equals 3x minus 4. And I want to find out, okay, what's the y coordinate when x is equal to 2? Rather than writing that sentence, I can just write like f of 2, right? Which is nice and convenient and compact. So the fact that f of 2 is equal to 2 would imply to me that 2 is a point on the graph of that function, or that 2 is a solution to the two-variable equation y equals 3x minus 4. Either way of kind of phrasing it is appropriate. Or they could mean, mean equivalent things. Or that line of, their equivalent statements. That's what the phrase I'm searching for. So again, mostly review concepts here, right? One of the things I'm trying to also do along the way is just to make sure that notation-wise, we remember what things mean. One of the things that can make mathematics difficult is there's a lot of language, there's a lot of notation, there's a lot of vocabulary, and if you're fuzzy on some of it, you'll get by for a while, but you might miss some big idea that becomes a hindrance later on. And if you add up a lot of those hindrances, things become really hard, right? So I just want to go back through here and hit on some of these big ideas and some of these notations and vocabularies and make sure we're kind of all at the same place so that when we build forward out from this, that we're kind of all moving from a solid foundation. We don't have any of those little gaps or misconceptions or holes or anything. But that's the first section there. In section 2, we're going to talk about domains and ranges. So if you remember from our definition of a function, a domain is a set and a range is a set. So when we write down a domain or range, what we're going to be doing is describing a set. Now there's a couple of different ways that you might describe a set. Sets can be discrete, like the set that contains just the numbers 1, 2, and 3. We would write that one way. Or sets can be continuous, that contain like all the decimals between 1 and 2. So like 1.1 and 1.01 and 1.001 and all the decimals in between 1 and 2. If any part of our set is continuous, one way to describe that set is with interval notation. And that's what we're going to talk about here. So the format for interval notation is we have a lower bound, comma, upper bound. And I'll talk about what I mean by lower bound and upper bound in a moment. And then at the end, we're either going to have a parenthesis or a bracket. And that parenthesis or bracket is depending on whether that upper bound or lower bound, respectively, is included in the set. Oftentimes, if the set is formed using an or equal to inequality, you'd have it included. Or the parenthesis is not, would indicate that that value is not included. Again, there you'd have strict inequalities. And the same thing at the upper bound. I'm not going to rewrite that information, but the bracket and parenthesis mean the same thing at either end, right? Included. So let's look at a couple of sets and then write the interval notations for those sets, just as some practice. Again, we used interval notation quite a bit in your Algebra 2 class, but it's been a minute. So let's just make sure we get a little bit of practice in and get everybody backfiring on all cylinders. So let's say that our first set we'll look at is the set of x's that is less than or equal to 2. So first thing I like to do is think about, okay, what numbers are we really talking about here? So we have 2, and we'd have like 1.7 and 0 and negative 5.3 and all keep on going down, right? Everybody good with what less than or equal to 2 is? I know that's kind of redundant, but just want to make sure. So first thing I'd want to do is find the lower bound for this set. So the lower bound is going to be a value that's less than or equal to everything else in the set. Since this one is x less than or equal to 2, is that lower bound like an actual number? No, right? Because any number you pick, I can give you one smaller. So what would we really write there for the lower bound? Negative infinity. Very good. The upper bound here is a number that's bigger or equal to everything in the set. Here that would be 2. Now the infinities always get a parenthesis because it's not an actual number. And then since 2 is less than or equal to 2, that value should be included in our set, so we put a bracket there. And this is how we would write our answer last year, right? Now I'm going to ask for a little bit more this year. We're going to be a little bit more precise. Since the variable in question is an x, I would also like you to include specifying that what we're saying is x would be a member of this set. So that symbol there is like an E with the corners rounded. Instead of having square corners, we'd have round corners on that little symbol there. But it just means it is a member of the set. And then what a set would follow. Okay? Again, this is not uncommon with math notations. Usually we'll start with like the minimal amount to communicate the first time you see it. And as you go, we'll ask you to be a little bit more specific and a little bit more specific and build up that notation as you go. Just like when you learn a language, it's not like we're learning grammar on the first day. It's like we want to learn the letters first. Same kind of thing with math notation, is we're just going to kind of start minimally and then add in as we grow it out as we go. Next example, -5 is less than y, which is less than or equal to 10. So this is a compound inequality, right? This is saying that y has to be greater than -5 and also less than or equal to 10. So this is the numbers like -4.9, -3, 0, 1.7, 6.8, 9.9999, 10. Everybody feel okay about what we're talking about here? The lower bound in this case should be then -5. The upper bound should be 10. Okay, the -5, should it get a bracket or a parenthesis? Parenthesis. And the 10 should get a bracket. And again, we need to do this case y is a member of, since the variable in this problem is a y. Any questions so far about what we've done? Again, if I'm doing anything or going too fast or speeding through something, you're like, I missed that, or I don't get that, or like, I'm not sure, what did you just do? Feel free to stop and ask. If I don't hear from you, I'm going to assume that everything is good and just keep on plowing away. But don't be shy. We'll do another compound inequality. This one is an OR inequality, as it clearly is labeled there. So this is saying a is less than -2 or a is greater than or equal to 5. So you have like two distinct inequalities here. So the numbers included in this set could be things that are less than -2. So like -2.5 and -10 and -58 billion. Or they could be things that are greater than or equal to 5. So like 5 and 7.3 and 10,982 and yada, yada, yada. So to do this, I'm going to need two distinct intervals, one for each inequality. So we'll start with the first inequality. What's the lower bound for a is less than -2? -infinity. And the upper bound? -2. And the infinity always gets a parenthesis. The -2 should get parenthesis. And then the symbol that we're going to use to connect these two inequalities is going to be the union symbol. So that looks like a capital U with no tail on it. It just means or in the language of sets. So it's a symbol we use to relate two sets together. It just means could be from this set or it could be from that set. So let's look at the next inequality and write the interval for that. So a is greater than 5 or greater than or equal to 5. The lower bound is 5. The upper bound is positive infinity. The 5 should get a bracket and the infinity should get parenthesis. What was I going to say? With the positive infinity, I write the plus sign there. It's not necessary that the plus sign is on the positive infinity. It's not wrong if you don't include that. I include it just so it reminds me that every time I write an infinity, there's a symbol that goes in front of it so I don't forget the negative. Where if you drop the negative on the infinity, that would be incorrect. But the positive doesn't need to be there. We feel good. Okay. So let's do some domains. Here we're going to actually see a piece of vocabulary that we didn't see in Algebra 2. So I'm going to talk about the difference between an implied domain and a relevant domain. In our Algebra 2 class, almost everything we did was looking at relevant domains. Most of the time when we were looking for a domain, it was like, what's the domain of y equals x plus 5 over x minus 4? You know, it would be a question like that, right? Almost all of our Algebra 2 questions when we asked for a domain was like, here's a function without any context, find the domain for it, right? So the relevant domain is going to depend on the specific operations involved in your function, right? Is there something that causes parts of it to be undefined? Because we can't have those parts in our domain. The implied domain comes from the context of the question. Now, if there is no context to the question, like just find the domain and then here's your function, in a class like this, the context would tell us that the implied domain is just the real numbers, right? But if you were provided some kind of context to the question, like say, the function f of x equals x represents, where x represents the number of people needed to screw in a light bulb. There we have some context, right? Doesn't make sense for x to have any real value because x is representing people, right? The number of peoples. So negative person makes no sense, right? That's not an amount of people you can have. Or decimals of a person doesn't make sense. You can't have like 7/8 of a person. So here you would say that in that context, the implied domain would just be like the natural numbers, so like 0, 1, 2, 3, etc. So we have to be a little bit careful when we're provided some context. We have to use some common sense and think about what the implied domain is here. And then we can move on to the function, look at the actual operations and decide, okay, of this implied domain, like do we have to throw out any of that stuff because it makes something undefined or whatever. So the relevant domain will always be a subset or equal to the implied domain. It'll always be, at most the implied domain. The relevant domain could never be a bigger set or include more stuff. Everybody feel okay with the difference between those two? All right, let's grind through a couple of examples. So here we have f of x equals 2 times the square root of x minus 4. Here we're given no context, right? We're just given a function and asked to write the domain. So the implied domain here is just all real numbers, right? There's nothing to do there. To do the relevant domain, I'm going to look at the operations that are involved in this function. So when I look at this, I see 3 operations. I see multiplication. I have 2 times the square root of yada, yada, yada. I see subtraction because I have the square root of x minus 4. And I see a square root. So 3 operations. Everybody good? See the 3? So what I'm going to do now is I'm going to think about, okay, if I have 2 real numbers and I multiply them together, can that ever give me an undefined result? No, right? If I multiply 2 real numbers together, I get a real number back. Well, what about the subtraction? Can I subtract 2 real numbers and get something undefined? No. Okay. So that one's fine. How about a square root? Can I take the square root of a real number and get something undefined? Yes. What kind of numbers give us a problem? Negatives, right? Remember, the square root of a negative number gives you an imaginary result, a non-real number answer. So that's the place where I need to concern myself. So to calculate the domain, I'm just going to take everything that's underneath the square root and say that it has to be non-negative. Everybody feel okay with that? So I can solve that inequality just by adding 4 to both sides. And I can represent that inequality using interval notation now. Since this is a domain, I'll say x is a member of. Here we have x is greater than or equal to 4. The lower bound would be 4. And the upper bound would be positive infinity. infinities always get a parenthesis. And because 4 is greater than or equal to 4, the 4 gets a bracket. No big deal, right? You might have also remembered the rule, recognize this as like the square root function, or remembered a rule that we use to find the domains of square root functions from algebra 2, but like that required memorization, and I prefer to like start concepting things out for us so that we're less reliant on memorizing rules and a little bit more reliant on like using our math knowledge rather than like memorizing stuff, which I think like as things get harder and harder and harder, it becomes more and more difficult to memorize. And like the more conceptualization you can do, the easier things, well, it keeps things from getting like overwhelmingly reliant on memorization. Like I'm bad at memorization. It's not a learning strategy that I prefer, even though I can learn things relatively well. But if you give me flashcards, it does not help me memorize them. Like do 100 problems, like I'll memorize the heck out of whatever's involved in doing those. But okay, our next one, again, no context here, so the implied domain is still all real numbers. When I look at the function here, g of x, what operations do we see going on? Anybody? Multiplication. What else? Addition. What else? Division. Those are the three that I see. Multiplication we've already established. No big deal. Not a problem. Addition of two real numbers? Fine. Division? Zero is a problem, right? Can't divide by 0. So I'm going to take everything in the denominator and say that that cannot equal 0. Everybody good there? So I'll solve that, just subtract 2 from both sides. But what I'm left with is not an inequality, which is what I would prefer if I'm going to write an interval notation for this. So let me think about what x cannot equal -2 means. That means that x could be anything that's less than -2, or x could be anything that's greater than -2. Everybody agree with that? That means the same thing as x not equal to -2? That's a nice little trick to turn something like that, where it's a not equals to, into inequality, so it's easy to make the interval for. And now that we're in this form, it's easy to write the intervals for it, right? So we have negative infinity to -2, union -2 to positive infinity. And again, we should have x as a member of that set. Now I buzzed through the interval there. Was everybody still okay with how we got that at the end? Again, if I'm going too fast, ask me to slow down, or if there's something you didn't quite get, ask me to repeat, or just if I don't understand something, like ask me to clarify. Totally fine to do any of those things. Sometimes I just get excited and get ripping and roaring. Sydney.
So how do you know what the implied domain is?
So if there's no context to the problem, like if it's not a story problem, it's all real numbers.
Okay.
So look at the next example where I do give you some context, and then we'll see the difference here. So here our function says v of s is equal to s cubed, where v of s is the volume of a cube with edge length s. Here there's definitely some context, right? I can tell from the form of my function that s is my independent variable, so that's what I'm going to be worried about for my domain. So I'm going to worry about the s's. And what quantity is the s representing in this? The edge length of a cube, right? So what are feasible edge lengths for a cube. Can that be any length? Has to be positive, right? Well, depending on how we want to define a cube, maybe we even want to say non-negative, right? Do you want to include something with 0 volume as a possibility? Depending on what your function is doing, that might be something worth having in. I'm not going to quibble on a problem like this. I wouldn't mark it wrong whether you included 0 or did not include 0, because we didn't really give you enough information about how we're defining a cube. Depending on the definition you use, a 0 length sided figure, you could count as a cube or you might not, depending on what you're using it for. For the sake of picking one, I'm going to pick to include 0. But here's one where, like, the implied domain you came up with just from the context. Use a little bit of common sense and like, oh, the edge lengths of cubes can't be negative. And whether you want to include 0 or not, I wouldn't mark it wrong either way. Everybody's okay with that? Okay. The relevant domain, then, I'm going to look at the function. What operations are involved in this function? An exponent, which is really the same thing as repeated multiplication, right? S cubed is just s times s times s. Is multiplication ever a problem? No. So what does that tell me? The relevant domain just has to be the same as the implied domain, because I don't lose anything from the operations involved. So this was one where if I ignored the context and just looked at the problem, you would have written down the wrong relevant domain. You know what I mean? We get the implied domain idea, though, just using common sense based on the problem. If there's no context, it's just all real numbers. Okay. Let's talk about range now. So we'll take a similarly abstract or algebraic approach to determining ranges. We're going to not rely on like rules on how to do this, or like memorization of a rule how to do this. We're just going to kind of reason it out a little bit in our heads. Everybody good? In general, this is going to be more difficult than finding the domains, because the range kind of depends on the domain, because we're talking about the y-coordinate, which is the dependent variable. It depends on x anyways. The way I like to think about this is I like to think about, okay, what I like to do is start by identifying the parts of my function that are increasing and what parts of my function are decreasing. So let's just kind of remind us what increasing and decreasing looks like. So let's say that this function is f of x. This function is increasing because if I move from left to right along the function, it's going up. Everybody cool? Remember that definition? Again, that's not the formal definition, but it's good enough for what we need to do here. The domain here is going to just be the interval from a to b. Hopefully that's easy to see from the graph. Notice that I have a filled-in circle at A and an open circle at B. That indicates to us that the point at A is included and the point at B is not. That's why I have a bracket on the A and a parenthesis on the B. Sydney?
What's up of the y?
That just says INC. It's just me indicating that this was the increasing function.
Oh, okay.
So if I wanted to write the range for this, the range is going to be the y-coordinate at A up to the y-coordinate at B. Everybody agree with that? So the way we write that is going to be f of A is going to be the y-coordinate at A, and f of B is going to be the y-coordinate at B. Everybody good there? Now, because A is a filled-in circle, and because the A in our domain that we're plugging in is included, the y-coordinate that we generate from A should also be included. Same as the y-coordinate B should not be included. Everybody feel okay there? Now let's do a similar exercise with like a decreasing function. So again, should be easy to see that that's decreasing. I'll call that one g of x. My domain is c to d. Hopefully that's easy to see. And now if I do my range, the range is about the y-coordinate. The lowest y-coordinate actually occurs at d, right? So I'll say the y-coordinate then would be g of d, right? That's the way we write the y-coordinate when x is d. And the highest point, the upper bound, would be g of c. Now notice that g of c, or at c, the point is filled in, so that needs a bracket. And at d, the point is open, it needs a parenthesis. Notice that's matching the c and d from the domain, right? The end, the parenthesis or bracket on d is the same as the parenthesis or bracket on g of d, even though they switched order. Everybody's okay with that? So what this is telling me then is basically I can figure out the range if I can figure out the parts that are increasing and decreasing. I can just kind of piece the range together from those. So let's go ahead and look at a couple numeric examples now. The big takeaway though is that, like, for decreasing, I'm going to use the lower bound of the domain to get the upper bound for the range, and the upper bound for the domain to get the lower bound for the range. But for increasing, they're the same. Upper bound for domain gives me the upper bound for range, and lower bound for domain gives me lower bound for range. I'm going to use the same three functions that we just worked with because we already have the domains for them. So this is like my example. The first thing I would want to do is to determine whether this function is increasing and decreasing. Ideally, it would be always increasing or decreasing. If it's not all the time, then it becomes a little bit trickier, but still doable. I would just break the domain into the increasing part and decreasing part and deal with them separately. But here, if I think back to my Algebra 2 class, I'd recognize this function f of x as a square root function. And I know the graph of a square root function, what that looks like. You know, it's either going to look something like this, you know, or like something like that, right? Okay, no big deal on that. Do you remember when we get the red graph, how to predict that? We just need the leading coefficient to be positive. In this case, the leading coefficient is the 2. So this is increasing. And here, the leading coefficient is, the blue graph would be when the leading coefficient is negative. If you didn't remember what the shape of a square root graph looked like, what could you do? Graph it on your calculator to just take a peek and go, oh, okay, increasing. Cool. Everybody cool? Okay, let's continue. So since this is increasing, the lower bound for the range is going to equal g of the lower bound from the domain, which in this case is 4. So I have 2 times the square root of 4 minus 4, which is just 0. Everybody okay with that? And the upper bound for the range is equal to g of the upper bound from the domain, which is positive infinity, which seems weird to plug into a function, and it is a little bit, but we're just going to kind of use some common sense to evaluate this out. So we have 2 times infinity minus 4. Well, if I have infinity and I subtract 4 from it, what am I really going to have? Still infinity, right? That doesn't affect anything. If I have infinity and I square root it, what am I still going to have? Still infinity, right? And I take infinity and I multiply it by 2. Still infinity. Now, the question here becomes, does this need to be a positive infinity or a negative infinity? Because I'm finding an upper bound, I know it's always going to be a positive infinity. If it was a lower bound, it would always be a negative infinity. And if we think about that, it should make good common sense. If the lower bound is, or the upper bound is something that has to be bigger than everything else in the set, and my upper bound is negative infinity, which is bigger than nothing, my set is empty, which I can't have if I had a domain, right? So it should make sense as to why that rule. Is that okay with everybody? Cool. Okay. So now we just need to piece this together. So I'm going to have 0 to positive infinity is my lower and my upper. Now what I need to do to determine whether they're brackets or parentheses, I look at my domain. So to get the 0, I did g of 4. And since 4 had a bracket, 0 should have a bracket. Likewise, to get my upper bound, I did g of infinity. Since infinity had a parenthesis, g of infinity should have a parenthesis. So not too bad, right? And I showed a lot of work there. All of that work isn't necessary. You could just write like, g of 4 equals 0 and g of infinity equals infinity and just move on about your day. You don't need to show like all these nitty-gritty details, but they're notes. And I tend to over-explain in my notes so that when you look back at it, you're able to kind of follow it a little bit easier than if I just write the minimal amount of work. You know what I mean, guys? You can get it. Oops. Okay. So this is my next one. Again, I'm going to start by trying to figure out, is this function increasing and decreasing, or where is it increasing and decreasing? So I'm going to think back to my Algebra 2 class. If I look at that function, that's a simple rational function because it's a degree 1 polynomial over another degree 1 polynomial. So I know for a simple rational function, I'm going to have like one vertical asymptote and one horizontal asymptote. It doesn't really matter where they are in terms of like the increasing and decreasing part. So I'm not even going to really worry about that. In this case, the vertical is at -2 and the horizontal is at 3, but like it doesn't matter for what we need. And then I remember that the graph then has like two hyperbolas that are always like kitty corner to each other. So like you'd either have something like this in the blue, or you'd have something that looks like this in the green. Everybody okay there? Does anybody remember how we can tell whether they're getting blue or green? You have to look at the ratio of the leading coefficients. So if the leading coefficient over leading coefficient is positive, you're getting the green graph. And if the leading coefficient over the leading coefficient is negative, you'd be getting the blue graph. Here our leading coefficient on top is 3 from the 3x. And on bottom it's 1 from the 1x. So we have the green situation. If I look at the green graphs as I start at one end and move to the other from left to right, we're going down in both arms. So I know that this is, let's use the same color, decreasing. Everybody okay with that? Again, if you didn't remember what the picture looked like, what could you do? Graph it on your calculator, right? Not wrong to do that. But again, I like to tie it back together to stuff that we already kind of know. It's good review, if nothing else. All right. Since this is decreasing, I know that the upper bounds and lower bounds are going to be switched. So my lower bound for the range, the first part, is going to be g of the upper bound of the, the upper bound of the domain in the first part. Make a u that looks less like a 4 there. And the upper bound for the range in the first part is g of the lower bound for the domain from the first part. And then the same thing for the second part, right? Is everybody okay with the notation that I wrote there? So I used the 1 to just indicate, like, you know, this is lower bound domain 1 is the negative infinity, for example. It's not, I mean, you don't have to use this notation. I just wanted to include something in your notes so you know where I'm pulling these values from. All right. So this is going to be g of negative 2. This one will be g of negative infinity. This one will be g of positive infinity. And this one will be g of, negative 2. Which is not too bad, considering we're going to get the same answers in a couple of places here. That's pretty nice. So g of negative 2, 3 times negative 2, for negative 2 plus 2. That gives me negative 6 over 0, right? Now, what is dividing by 0 really representing? We know that we say that's undefined. Yeah, so if I want to divide something into no parts, I would need to chop it up like infinitely much, right? You guys buy that? They're like, if I'm going to take 6 things and divide it into 2, there are going to be 3 in each piece. If I'm going to take 6 things and divide it into 0 parts, there's going to be like infinitely many pieces in each part, right? Because we've chopped it up so finely. Everybody okay with that idea? So this is really telling me infinity when I'm dividing by 0. And since we're talking about a lower bound, what type of infinity do we have? Negative infinity. Okay. We'll do g of negative infinity now. So negative infinity plus 2 is still just negative infinity, right? And negative infinity divided by 3 times negative infinity divided by negative infinity can cancel the infinities to just give us 3. Everybody's okay with that? Very tempting to say 3 times negative infinity is negative infinity again. Try not to, to make that misconception there. It's a little bit tricky. Since there's division going on, we also have to worry about that. So if I go down, I don't really need to do this one, right? That's still going to give me 3. Everybody okay with y? Okay. And I don't really need to do this one because I know it's going to be infinity. But since it's an upper bound, this time it's a positive infinity. So now I just need to piece this together into into my range. So my first interval is negative infinity to 3. And my symbol on the negative infinity should be the same symbol from the domain as the first negative 2. So that's a parenthesis. And my symbol on the 3 should be the same as the symbol on the negative infinity from the first part of the domain, which also is a parenthesis. And then I'll have my union. and then I'll have 3 to positive infinity. And again, coming from the positive infinity on the domain is a parenthesis, and coming from the -2 on the domain is a parenthesis. So everything gets parentheses, and there I go. Which is not too bad, right? For something that like looks kind of confusing. But we'll try to do it in a way that like is systematic and uses not much more than like common sense. Yes, sir.
So for this one, you said it was decreasing, right?
Decreasing, yeah.
How did you figure that out?
So I just looked at the graph. We decided it was the green part, right? So as I'm moving from left to right, it's going down. So that's all I'm doing is just looking at the picture.
Okay.
So each part, as I move from left to right, it goes down. That's all I need. Cool? Cool. Yeah, that one had a lot of stuff going on, right? This one's a little easy. Actually, this one I think is the easiest one. Does anybody remember what the graph of y equals x cubed looks like? Just kind of looks like that. Again, if you didn't remember that from last class, what can you do? Graph it on your calculator. The takeaway, though, is what do we see here? It's increasing, right? That's the big takeaway. Because if you move from left to right, it's moving up. Right? We always read a graph like we read a sheet of paper from the left side to the right side. Sydney, you're making some faces. Are you okay?
Yeah.
Okay. Just checking. Okay. Since it's increasing, I know the lower bound for the range is going to be v of the lower bound for the domain, and the upper bound for the range is going to be v of the upper bound from the domain. So this will just be v of 0, which is 0 cubed, which is still 0. And this will be v of positive infinity, and positive infinity cubed is still positive infinity. So my range is going to go from 0 to positive infinity. Since the 0 comes from the lower bound, which was a bracket, the 0 gets a bracket. Yes, sir.
So, like, there's implied domain. Is there like an implied range? Like, there's relevant.
Sure. So, like, you could think about it that way. Yes. Really, you could say every implied range is all real numbers.
Gotcha. Okay.
But, you know, like, because that's really you're mapping from some restricted set, you could map it everywhere. You don't know, you know. Sydney?
So to find out what goes before the number of, is it just whatever is before the equal sign in the original equation?
Right, yeah. So the ranges are y's. I used, since this isn't like x and y, you're not plotting x and y, you'd be plotting s and v of s on your table or on your graph. I used v of s there. If you put y there, I won't mark it wrong.
Okay.
But I'm just trying to be precise there. But yeah, that's a good question, a fair question. Okay. Yes, sir. Paul. Yeah, absolutely.
Lower bound of range.
Mhm.
It's a lower bound of domain, and it says it's equal to 0. How do you get that?
So the lower bound from the domain is this, right? Because the domain is always lower bound, comma, upper bound, right? So this 0 is coming from there, and this positive infinity came from there.
That makes a lot of sense.
Yeah, no problem.
Can you go
Jordan.
to like
Okay.
the last one?
Yeah.
How'd you get infinity for like the like,
This one? I just said, we already did g of negative 2. So I just copied the answer.
But the other one.
Right. So remember when I assigned the sign on the infinity, it depends on whether it's an upper or lower bound. Since that one is upper, it's positive instead of negative. Yeah, no problem. Again, these details matter. These are good questions. You know, like if you missed when I said it, because we're not doing a lot of work to do these. We're like saying a lot of the reasoning aloud and not writing it down. If you missed that detail, like those are important details. Like, please ask a clarification. Totally fine to do that. It's good to do that. It saves us time later if you get it today rather than do a bunch of homework and get confused on the homework and have to come back and do all the problems again. You know, like, not a big deal. I'd rather do it well today. Right. The last section we're going to do today is a new idea called continuity, but it's not a difficult idea. We've already kind of touched on it when we talked about continuous sets, where the sets have like everything in between the two values would be a continuous set. A continuous function is something you can draw without having to pick up your pencil. Okay? So if you can draw the curve without having to pick up your pencil, that would be a continuous function. Sydney? Continuous? Yeah, we've seen a couple of ones in Algebra 2 that weren't. I'll do some examples here of some types of discontinuities then. So any break in our function is called a discontinuity. There's 3 types of discontinuity. And we'll look at some example. We'll look at first what some graphs are, and then we'll give you some like function examples. After that, oops, really types. So the first one is called the removable discontinuity. Maybe that rings a bell from Algebra 2. This was something that could happen when we graphed general rational functions. So here, there's like a hole in my graph. There's like 1 point missing. And it's still considered a removable discontinuity if like we have the hole, but we've replaced it or we've put it in the wrong place, right? There's still a gap, but it's just we've picked that point up and moved it somewhere else. Now, keep in mind that point where we've moved it to has to be on the same vertical line as the hole. Why? Yes, sir?
Well, because it can't move by the domain because then it wouldn't pass the vertical line test.
Very good.
Right now it does.
Yes, very good. Yeah, so if that point wasn't directly lining up with the hole, the gap in the function, you would fail a vertical line test and you don't have a function anymore, and then somebody's sad. Okay. Another type is an infinite discontinuity. So what this looks like is something we've also seen before. So your infinite discontinuity is just like a vertical asymptote. Now, not all vertical asymptotes are infinite discontinuities, but every infinite discontinuity is a vertical asymptote. Can anybody think of an example of a vertical asymptote that is not an infinite discontinuity? Sydney? You would have seen this last year in Algebra 2. A whole class of functions have them. It's probably something you did at the end of the year and is usually something that doesn't stick very well. Logarithms. Think about the graph of the logarithm starts with a vertical asymptote, and then you draw the whole curve without having to pick up your pencil. So that's an example of a vertical asymptote that's not an infinite discontinuity. But here we see an infinite discontinuity that is a vertical asymptote. So there's more vertical asymptotes than there are infinite discontinuities, but they are subset relationship. Okay? Of course, yeah. The last type of discontinuity is the jump discontinuity. So what this looks like is something like this. And actually, let's do that. So keep in mind, when these line up vertically like this, only one of them at most can be filled in. You can't have both filled in, but both could be empty. That would still be okay, still passes a vertical line test. And you could have both ends filled in, but you'd need to have like some horizontal gap in between them, right? Like that's okay because they're not lined up vertically from one another, obviously. So jump discontinuity you would not have seen before, likely. So that's what the graphs kind of look like, or examples of what these different types of discontinuities look like. Most of the stuff you graphed last year didn't have discontinuities in it, right? Really, the only thing that had any discontinuity were the rational functions. Those were the only things that you saw last year that had any kind of discontinuities in it. So let's just do some examples of functions. So let's just make it, actually, let's just do it up here. I'll write it next to it because I drew these things that were matchable. So this thing, an example of what this could be, I'm going to write this in factored form because it's a little bit easier to see what this is. But if you had that, oops, one of those needs to be a negative. If you had that general rational function, that's pretty sloppy there, Kulik. That would generate this graph, right? You remember that for removal discontinuity, you need to reduce something completely from the denominator. So here the x plus 3 reduces out, so you'd have a whole at x equals negative 3, which is about what we see there. And the remaining graph is just the parabola x squared minus 4, when you FOIL out x plus 2 and x minus 2. To get something like this, you'd have to use a piecewise function, which you didn't or haven't talked about before. But a piecewise function, you kind of write this way and you say, okay, for we do something for this part of the domain, and then we do this for another part of the domain, and you can have as many pieces as you want. And the f of x here that I'm describing is just the same f of x from over here. I just didn't want to write that again because that was a lot of symbols to write. Is that okay? For this one here, this could just be like a simple rational function. So this could be like 1 over x plus 2 and then plus 3 or something. Remember, the vertical asymptote is tied to where the denominator is equal to 0. And the horizontal asymptote is tied to the plus 3 at the end for a simple rational function. So that's an example that would give you a graph that looks similar to this. And a jump discontinuity, you also have to use a piecewise function. So I think we're at I now. So let's see, that would be like negative 2 square root x minus 3 when x is, probably like minus 1. When x is less than 3. And then here it would be like 2, that should be 3 minus x. Beep. And then this one would be x minus 3, and then like, I don't know, plus 4 or something, when x is greater than or equal to 3. So like this piece is described here, and then this piece is described there. It's basically what you're doing with a piecewise function. It just tells you how to graph the different pieces, and you just treat them as like this one graph, even though there's different parts all on the same axis. And I think that's good for today, guys. Your homework for next time, for the homework check, the first part of your homework check is 1 through 12. Remember, the homework check is Sunday at midnight, so there's no rush on this. Although if you want to ask questions, you should at least look this over before next class. So the problems you can find in the content library. You can do the problems in OneNote or on paper. It doesn't matter to me. Although if you are doing them on OneNote, please, please, please do your work like off to the side, like have the answer off to the side. Don't try to cram it in all right next to the problem and make it like impossible for me to read anything. Like use some space, make it legible. I do want to look at what you do. I do care at seeing your work and all that. So please try to be neat-ish. If you're doing it on paper, that's totally fine. Take a picture and drop it into the homework tab. If you need help doing that, come talk to me. I'd be happy to show you.